Hello, today I'm going to present my paper Maximization of a Pore Fluid Motion in Poroelastic Formation for Wave-Based Enhanced Oil Recovery. In this paper, I will first introduce what wave-based EOR is, then I will introduce my research question and hypothesis and research method and numerical result, and I will end by discussion by addressing research question. The basic concept of wave-based EOR is if we shake oil reservoir either by using surface ground wave motion or downhole wave sources, it can increase oil production rate. So a lot of tests, field test has been conducted in Russia and China and in the US. And the advantage of this wave-based EOR is it first indiscriminately stimulate the entire reservoir while other EOR methods such as gas or chemical flooding bypasses a low permeability area in highly heterogeneous reservoir, and it is suggested environmentally friendly. And the first dominant mechanism of a wave-based EOR is if we shake the oil reservoir, this vibration release trapped oil droplets in tiny pore spaces, and it coalesces them into larger one, which is more likely to flow in the pore spaces. And to this end, we need very large values of acceleration field. And as a second mechanism, if we shake the oil reservoir, this shaking induces cross-flow oscillation between low and high permeability area. And this cross-flow oscillation or fluid pressure oscillation extract remaining oil in low permeability area to the high permeability area. And in similar manner, the cross-flow oscillation induced by the wave between the fracture and the surrounding rock matrix increase extraction of oil from the rock to the fracture space. And in the past research, we showed that if we judiciously optimize wave sources, it can maximize wave energy in target oil reservoir while we can minimize unnecessary vibration in the ground surface. And in the next research, we consider the poroelastic formation and bio wave model. And in this next research, we try to address this research question. First one is what is the optimal loading time signal that can maximize relative wave motion of a pore fluid? And the second question is, are there any amplification frequencies corresponding to maximum relative wave motion of a pore fluid? And the third question is, what is wave-induced incremental volume of oil extracted from an oil reservoir? So to answer this question, we try to test the following hypothesis. The first hypothesis is if we use inverse source modeling, we can find optimal force signal that can maximize wave motion of a pore fluid. And as a second hypothesis, if we use hysteresis model of pore fluid flow behavior and build wave solution, we can estimate the incremental volume of vibrationally mobilized oil. And this is the objective of first research method, inverse source problem. The basic idea is this. Let's say we discretize the force time signal by using quadratic shape function. And we try to find each values of discretized force parameters that will minimize this objective functional. And by minimizing this objective functional, which denominator is a spatial and temporal integration of kinetic energy in terms of relative wave motion of a pore fluid, we can maximize wave motion in target poroelastic formation. As a second method, we use a high hysteresis model of a pore fluid flow behavior, which is otherwise called one-way valve model. The key idea of this model is in the flow coming from low to high permeability area, there is more oil than in the flow flowing in the opposite direction. And based on this behavior, this characteristic of this pore fluid flow, we can estimate how much oil is extracted from low to high permeability area. So this is governing wave physics that we consider in this research. First, we consider Biot wave model, and Biot wave model use all these material properties, and Biot wave model use displacement field of a solid rock matrix, which is U, and relative displacement of a pore fluid, which is W. And we also consider just simple, elastic wave equations for non-permeable surrounding medium, and the traction boundary condition, and wave observing boundary condition in the bottom to truncate this infinite medium into finite medium. And we also consider interface condition between this poroelastic formation and non-permeable medium. Which is displacement and total stress continuity condition, and the zero flux condition at the interface and zero initial conditions. And this is examples of a forward solution. Here we consider these recurpers at the traction, and we consider this 4-layered medium where the third layer is poroelastic formations. As you can see, we were able to obtain the wave solution of U and W and the total stress and pore pressure at each different times. So to tackle this inverse source problem, which is in terms of a large number of control parameters, we use what is called the PDE constraint optimization approach. The basic idea of this method is we impose the governing PDE and boundary condition into what is called the augmented functional by using Lagrangian variable. And the optimality condition of this augmented functional is if we satisfy state problem and adjoint problem and control problem, we can find optimality condition. And here state problem is the problem identical to the original governing wave of physics, and adjoint problem is problem very similar to original wave of physics except for the body force term and the final value conditions. And to solve the state and adjoint problem, we use the classical mixed finite element method. And by using the control equation, we can use a gradient-based minimization scheme to solve this inverse problem. And control equation allows us to evaluate the gradient in analytical manner. And we verified our approaches by comparing the gradient by the control equation and by finite difference scheme. And both gradients were in excellent agreement. And these are the numerical result of optimization scheme. And here we started from this initial gas, and we converted it into this optimal loading, of which dominant frequency is 11.8 Hz when we discretize the force time signal by using 200 parameters. And if we increase this number of force parameters, we're gonna end up with we ended up with the optimal loading signals of higher frequency like this. And here This is our plot of objective functional by using the sinusoidal loading for different frequencies. As you can see, there are a lot of local minimum, and this local minimum corresponds to the dominant frequencies of optimized loading signal, meaning that our optimizers got it right in terms of finding minimum point. And this is the wave motion induced by optimized loading and non-optimized loading. Clearly, the wave motion by optimized loadings are much larger than the others. But this wave model has one drawback. The solution by Biot's wave model show that the pore fluid only moves back and forth. So there's no correlation um, between this wave-induced mobilization rate and the motion of oscillatory fluid from Biot wave solution. So to bridge this knowledge gap and or address the third question that I introduced in the beginning, we used this second method, which uses a hysteresis model of a pore fluid flow behavior. By using this hysteresis model, we consider this example formation model, where we have very high permeability area surrounded by low permeability areas, and we are going to estimate the incremental oil production, extracted volume of oil, volume of extracted oil from this low permeability to high permeability areas. As you can see, this mobilized oil volume per this cross-section area, which is 10,000 square meter, we showed that the volume of extracted oil could be very sizable within 1 day wave operation, wave stimulation operation. And there are some amplification frequency for this volume of mobilized oil, and this amplification frequency depends on the layering, the thickness or layering geometries of poroelastic formation. And we also saw that we can increase this volume of mobilized oil by increasing mobility of low permeability areas. So this is our summary of the answers of research question. The first research question was, what is optimal loading time signals? And is it feasible to identify them? And our answer is, if we use inverse source approaches, we can recover these optimal wave source signals, which can maximize wave motions of a pore fluid in targeted formation. The second question is, are there amplification frequencies corresponding to maximum wave motion of a pore fluid? And our answer is, our optimized time signal includes a single dominant frequency, and they are consistent with the amplification frequencies. And what is wave-induced incremental volume of oil extracted? Oil extracted from an oil reservoir. Our numerical result employing the hysteresis model show that the volume of wave-induced incremental oil production could be sizable, and the amplification frequency of this volume depends on layering of poroelastic formation and rock properties. And if we improve fluid mobility in low permeability area, it will increase the volume of this wave-induced incremental oil production. Thank you for listening, and this is the list of references.